Hello everyone, my name is Angela Brown and I will be presenting and discussing my Lab 5 report for Physics 2212. Lab 5 encompasses Faraday's law by exploring the interaction between a falling magnet and tube of aluminum foil. The bar magnet is the source of the external field and the induced current is driven by the tube of aluminum foil. The principles used throughout the lab are Faraday's law of magnetic flux, magnetic force, induced currents, and Curry electric fields. Biot-Savart's law of magnetic field due to a dipole, Newton's second law, and Newton's third law. The setup began by locating which end of the magnet was north using the Teslameter app. Knowing the field pattern of a dipole, which is shown to the right, I was able to deduce the direction of north. I was tasked with dropping the magnet through the tube of aluminum foil and filming it. After marking north and south on my magnet, I set up my phone on a tripod to get a clean shot in order to find the time. I recorded myself dropping the magnet 6 times in total. The average time was 1.1733 seconds, and my data for each child is in the chart below. I tested the time it took for the magnet to reach the ground in freefall, which was 0.32 seconds. Since there was no upward magnetic force on the magnet in freefall, the fact that the time is shorter follows the free body diagrams. Lastly, I measured the dimensions of my tube of foil. This is a video of me doing the experiment. On to the coding portion. First, I will discuss the different features of my code and then interpret the simulation and graph it produces. To the left, the constants are declared and properties of the graph are stated. I added my measurements of the aluminum foil in this section. To the right, the properties of the tube are created and I plugged in the mass of my magnet and the magnetic dipole moment from Lab 3. To the left, I plugged in the same function used in Lab 3 to find the magnetic field of the bar magnet. Then I created a function to calculate the d-flux through each ring due to the falling magnet. I followed the Faraday's law magnetic flux formula previously stated. To the right, the while loop is created for the loop simulation. I created the vector for the gravitational force, and then the d-flux is calculated from the ring due to the falling magnet. Lastly, I calculated the typical magnetic field at each ring by the following equation for the magnetic field of a loop, which is displayed to the right. Then calculated the magnetic force of the magnet and updated the magnet's velocity and position. Here is a video of the tube simulation. The simulation created this velocity versus time graph and expresses the time it took the magnet to fall through the tube as 0.93 seconds. Let's interpret the simulation. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. The red ring corresponds to a clockwise current and the blue ring corresponds to a counterclockwise current. I'm able to determine this through the right-hand rule. If I flip the magnet around, the magnet would fall faster because the induced current would be pointing in the opposite direction. The total time in the tube is less in the computational system than in my real-world system. The computational system will not have human errors like clumsy dropping techniques and inaccurate timing. The velocity versus time graph tells me that the magnetic force goes against the gravitational force, so that the change of velocity over time is much smaller. In conclusion, the simulation shows a more accurate calculation of the time due to simple human error during the real-world experiment. My data makes sense because the simulation calculated a time close but smaller than mine, but not smaller than the magnet in freefall. We are clearly able to see how the magnetic field has an effect on the falling magnet. For my final concept questions, my first answer was, if the resistance was 0, there would be no current in the conductor because I equals MEF over R. Since there would be no magnetic force upward, the magnet would basically be in freefall. For the second question, my answer was, the holes would make the magnitude of the magnetic force fluctuate between 0 and the max magnetic force. The magnet would fall faster, but not as fast as when in freefall.